Good evening, everybody. This is Keeping an Eye on the Universe. This is a short talk about what telescopes can tell us about how the universe works. Now, telescopes have been around for 400 or so years, and one of the first people to use a telescope and point it at the sky was Galileo back in the early 1600s. Back then, telescopes were made by using lenses to focus light, but more recent developments of telescopes have involved using mirrors rather than glass lenses because they are easier to make large. In other words, you can make a large mirror more easily than you can make a large lens. And in the last century or so, we've had telescopes with mirrors that are 2.5 or 5 meters in diameter. That's the Hooker telescope and the Hale telescope over in California. And of course, most people would recognize some of the telescopes that have now been launched into space, such as the Hubble Space Telescope, which is now more than 30 years old. And perhaps you know of the James Webb Space Telescope, which was launched relatively recently, less than a couple of years ago, on Christmas Day 2021. So we have a number of telescopes on the ground and telescopes in space. Under construction, we have some very large telescopes, such as this one, the European Extremely Large Telescope, with a mirror diameter of 40 meters. And it's a little difficult to keep in your head the difference between some of these smaller telescopes and the recent sized monsters that are being built that are many tens of meters across. To try and give you a sort of sense of scale, here's a little diagram in which various large telescopes are shown with the size of their mirrors, the mirror that collects the light. They're all to scale. And I'm sure you find it very difficult to relate to a human there. So just to give you a sense of scale, there's a tennis court down in the bottom left, and there's a basketball court down in the bottom right. So you can see some of these mirrors are absolutely huge. In the top left are some of the smaller telescopes I've just mentioned, like the Hooker telescope and the Hale telescope. The largest telescope in the world at the moment that's operational is that one at the top, with a 10-meter diameter. Well, perhaps not diameter because we're talking about hexagonal arrangements of small mirrors. But the largest telescope in the world currently is approximately 10 meters in diameter, and that's sitting in the Canary Islands. By comparison, the telescopes that have gone into space have relatively small mirrors. So you can see in the bottom left we have the Hubble Space Telescope with a mirror size of only 2.5 meters or so, and the James Webb Space Telescope with a mirror size of about 6 meters. Much smaller than the largest telescopes that exist at the moment, and very much smaller than the telescopes that are planned for the very near future. That's simply because it's difficult to put a large telescope into Earth orbit or to send it into space to do the astronomy that we want to do with these large telescopes. So I'm sure a lot of you will recognize that the Hubble Space Telescope has been in operation since about 1990. It's sort of coming towards the end of its life. They're not intending to retire it just yet, but it won't be too long, so keep your eye on eBay because it might be appearing before too long as a second-hand telescope, only one careful owner up to this point. And the Hubble Space Telescope has been in operation for a long time, and one thing it did a few years after it was commissioned is take a so-called deep field, which means point at a patch of sky in which you don't think there's anything interesting going on there, and take a really long exposure. The exposure here, they basically exposed the camera for about 10 days to catch as much light as possible in this, what they thought might be a blank area of sky. It turns out they picked up 1 or 2 stars that are part of our own Milky Way galaxy. Everything else you can see here is a more distant galaxy in its own right. Thousands of galaxies, some fairly close, some very distant. And you have to appreciate that the Hubble Deep Field, in fact the Hubble Space Telescope, only has a very small field of view, very small field of view on the sky. If we compare that with the apparent size of the full moon in our sky, which you can just about cover with one finger outstretched at the end of your arm, you can probably cover the disk of the full moon. But the field of view of the Hubble Space Telescope is tiny compared to the full moon. So you can see the patch of sky that Hubble is looking at is tiny. And if in that tiny patch of sky, it sees thousands upon thousands of galaxies, then we can infer that if the rest of the universe looks the same, then there must be many billions, possibly even a trillion galaxies out there in our observable universe. So the Hubble Space Telescope was a fundamental discovery in telling us something about the perspective of where we sit in the universe. Just to prove it wasn't a fluke, in other words, having picked one patch of sky and seen thousands of galaxies, just to show that they hadn't accidentally picked a patch of sky that just happened to be populated with lots of galaxies and maybe there were less elsewhere, they picked another patch of sky in the southern hemisphere rather than the northern hemisphere and took another deep field just to prove that, yes, it looks a little different, but it has the similar distribution of lots of galaxies, some of which are close, some of which are very, very distant. One thing you have to bear in mind with images like this is the larger galaxies might indeed be relatively close to us. A lot of the smaller galaxies that look extremely faint are probably very distant. And because light takes a finite length of time to travel any distance, the more distant galaxies, the light must have left a long, long time ago to reach us now. So in a sense, we're looking back in time for some of the galaxies in an image such as this. When we look at close galaxies, telescopes like the Hubble Space Telescope are able to show us the structure of some of our neighboring galaxies in amazing detail. This is a superb image of a so-called barred spiral galaxy. Spiral because of the spiral arms that you can see, and barred because it seems to have a large bar down the middle, and the spiral arms seem to be starting at the end of these bars. And an image of a galaxy like this on its own doesn't tell us very much, but if Hubble and other telescopes are able to image not just a few hundred, but many thousands of galaxies, then we can get an idea of how they're structured and perhaps how they came to be, the evolution that led to a structure like that. Hubble and other telescopes have shown images like this. It looks a little odd. You can perhaps see why it's called rose galaxies. In this case, it looks like two galaxies that are getting close enough to each other, or perhaps they've just passed each other, such that gravity of one is affecting the other. In other words, the spiral arms of this galaxy at the top look like they've been disrupted by the fact that there's another galaxy close by. And that seems to be much more likely to occur than we first appreciated. In the early days, we thought galaxies were just large objects, large collections of stars that are very much distant from each other. But now, the closer we look, the more we realize that a lot of galaxies are interacting with each other. The gravity of one is affecting their neighbors. In this particular case, it looks like two galaxies have actually collided with each other. Not quite as dramatic as it sounds, because if two galaxies collide, that doesn't mean the stars in one galaxy hit all of the stars in the other galaxy. On the contrary, they probably pass through each other with none of the stars actually hitting each other. But in this case, two galaxies seem to be very close to each other, and notice this large dark region that has lots of pink in it. Pink indicates the presence of hydrogen, and we think there is a riot of new star formation going on in these areas. So far from being a cataclysm when two galaxies collide with each other, it actually looks like that could be a sign of, if you like, rebirth, in that there's a whole load of new stars being born because these galaxies are interacting with each other. And we now think that this is an important part of how the universe came to be the way it is now. Lots of galaxies have interacted with each other. The Milky Way galaxy in which we live has probably interacted with other galaxies, and it might be swallowing up some smaller galaxies along the way, and that's part of how galaxies evolve. It is not, as it were, a fluke event. It's part of the natural evolution of galaxies over many billions of years. If we look at what's going on inside our own galaxy, we have a few 100 billion stars, and some stars end their life like this. This is a nebula, a cloud of gas, which is effectively the outer part of a star that's been thrown off when the star comes to the end of its life. When the nuclear fuel in the star ends, the outer part of the star can get blown off into the space between stars, the interstellar medium. And this is probably the fate of our sun. Not just yet, don't panic, it's not going to be for quite a few billion years, but eventually our own sun, when the fuel runs out in another 4 or 5 billion years' time, this is probably what's going to happen to our sun. The outer part of the sun's atmosphere is going to be blown off and produce something perhaps similar to this beautiful so-called helix nebula. Some stars, when they come to the end of their lives, they have more dramatic endings. If a star is really massive, when the fuel runs out, it doesn't just puff off a little bit of the outer atmosphere of the star, the star can blow itself to pieces completely. This is the so-called Crab Nebula. It's the remnant of a supernova that exploded. It was seen by the Chinese back in 1054. So as far as we're concerned, it went off about 1,000 or so years ago. And again, it's been possible to image nebulae like this for many a long year, but the detail available from the Hubble Space Telescope allows us to see an incredible amount of detail to get an idea of what's going on when a star goes supernova and what happens to all the material that's ejected into the interstellar medium. Another example of a supernova remnant is the so-called Veil Nebula. This inset shows an amateur picture of what this particular supernova remnant looks like. So here we have a supernova that went off probably tens, if not 20,000 years ago. And what we're seeing effectively is the bubble of all the material that was ejected from the star somewhere in the middle, not necessarily one of those dots. So a star went supernova, let's say 10,000 years ago. The material was ejected, and that material, again, has been plowing its way through the space between stars. This is a very large object in the sense that the size of the object in the sky, as we observe it from Earth, appears to be larger than the size of the full moon. It's quite a few thousand light years away, but that means it must be a huge object if it occupies quite a few degrees of our sky. It's actually far too big for the Hubble Space Telescope to image. Remember, the Hubble Space Telescope only has a relatively small field of view. If we were to look at one particular part of detail, just the detail inside that red rectangle, then we get this image shown here. You can see there's an enormous amount of detail, and physicists and astrophysicists are looking at images like this to try and understand, well, what was ejected when this star went supernova? The colors are not natural, they're not arbitrary. This particular image has been colored according to a particular color scheme. The color scheme was red corresponds to hydrogen, green corresponds to sulfur, and blue corresponds to oxygen for this particular image. That's not always the way they assign colors, but it was in this particular image. And so by looking at color images like this, we can get an idea of how the elements are distributed throughout space, and we can tell something about the nature of the supernova that produced this particular shock wave as it moves through space. And it also tells us about something about what it is that's floating around in between the stars. What is it in the interstellar medium? What atoms are floating around out there that allow us to see this effectively shock wave as it moves out from the original supernova? So exquisite detail visible in images like this. Perhaps you've seen a lot of images from Hubble that look a little bit like this. This is the conventional way that Hubble shows its images, where again, it's not natural color, but the red and the green and the blue in the image have been assigned to particular elements. In other words, they look at where the sulfur is and they make that red. They look at where the hydrogen is, they make that green. They look at where the oxygen is, they make that blue. And you end up with an image looking like this. This is part of a nebula that's in the southern hemisphere. It's called Eta Carina. Perhaps you're more familiar with its northern counterpart. This is visible from places like the UK. At higher northern latitudes. This is in the Eagle Nebula, and this is the famous Pillars of Creation. It was imaged shortly after Hubble was launched, and it's been re-imaged when it had new cameras, replacing the old cameras when shuttle astronauts went up to replace some of the spectrometers and some of the cameras. But when we look at an image like that, we think, well, something is going on inside these huge gas pillars. We think stars are actually sculpting these gas pillars, and it'd be nice to know what's actually happening inside, because beautiful though these images are, The Hubble Space Telescope, working in the visible part of the spectrum, finds it very difficult to see inside very dusty environments where there's a lot of stuff which scatters the light and stops us seeing detail inside. And that's why new telescopes have been launched. The James Webb Space Telescope, launched a couple of years ago, is designed to work in the infrared part of the spectrum because that gives us information which is a little different from the information we get if we look at what the universe is telling us in the visible part of the electromagnetic spectrum. So the James Webb launched on Christmas Day 2021. It was too large to go into the top of a rocket as was, so they had to basically fold up the mirror. That's what the mirror looks like when it's unfolded, but they had to fold the mirror in order to make it fit inside a package that could go on top of a rocket, and then it was launched into space. It's not actually orbiting around the Earth in the same way the Hubble is. You can see here the difference in size of these two telescopes. There's the schematic of the Hubble primary mirror, 2.4, and a rough size of the James Webb mirror made of smaller hexagonal segments to allow it to be folded. And it's been launched not in orbit around the Earth, but into a position, into a sort of parking point in space. It's that red dot there. It's a parking place roughly 1 million miles above midnight. Midnight is the part of the Earth that's on the opposite side from the sun, so that point there is midnight, and the James Webb Space Telescope is parked 1 million miles above midnight. And that's where it is basically going to stay for quite a while, whilst it spends its hopefully 5, 10, maybe 20 or more years observing the universe in infrared light. One of the reasons for looking at infrared radiation is to look back in time as far as possible. Remember I said that with the Hubble Deep Field, we can take an image and some of the brighter galaxies might be quite close, some of the fainter galaxies are probably more distant. But because the universe is expanding, any light emitted by these very distant galaxies, for instance, in the visible or ultraviolet part of the spectrum, because the universe has been expanding for billions of years, that light is getting stretched out. And so light that was originally visible light has now been stretched to longer wavelengths, and that's what we call infrared light. So how far back in time can we go? We think the universe was born in the Big Bang approximately 13.8 billion years before what we can say is now. So that's us here at 13.8 billion years after the Big Bang. One question we'd like to answer is, when did the first stars, when did the first galaxies form? Now we know that galaxies exist by looking back, for instance with the Hubble Deep Field. We can look back many billions of years and we know that galaxies have existed for a long, long, long time. But if we want to know when the first ones were made, we have to look right in that first 1 billion years of the history of the universe. And if I just expand that first billion years and show it as hundreds of millions of years here, the Hubble Space Telescope, if it takes a really, really long exposure and looks at the faintest galaxies it can possibly see, it gets back in time to approximately 500 to 600 million years after the Big Bang. But at that point, stars and galaxies already existed. So the question is, when did they come into existence? Surely it would have taken a little bit of time after the Big Bang, which we believe was the beginning of everything. Surely it would have taken a little bit of time for the first stars to form and the first galaxies to form. It is hoped that we can push that even further back with the James Webb Space Telescope. By looking in the infrared, it sees some of these distant galaxies, it sees the light that's been stretched by the expansion of the universe, and so it might be able to see even fainter galaxies than the Hubble telescope. And maybe we could get down here somewhere. At the moment, we're not quite there. The James Webb Space Telescope is producing some interesting images, and we're starting to see stars that seem to have been born around this time. Maybe we can push that back a few 100 million years. Keep watching the news for seeing what James Webb is producing. When it first was launched a few months after it was operational, it released a few images, some of which you perhaps recognize, some part of the Eta Carina Nebula, some galaxies, etc., that are interacting with each other, some planetary nebula, again, a star that shrugged off its outer atmosphere, similar to the one I showed you earlier. And it spent some of its time looking at nebulae such as this, a nebula again in the southern hemisphere, where a bright star seems to have carved out a little bubble within this nebula. Pictures and spectra obtained at different wavelengths of visible or infrared light allow us to get an idea of how these stars work and how they interact with the nebula around them. This is one of the most famous pictures that James Webb has taken. Perhaps you don't recognize it until we pull out slightly, and then we realize it's a very high-resolution image of the familiar pillars of creation. Remember, when we looked at that with the Hubble Space Telescope, we couldn't really see what was going on inside these pillars. We assumed it was stars that are sculpting these pillars, these gaseous pillars, but we couldn't really tell. If we actually put them side by side, that's simply an image taken with the James Webb with a slightly different color palette, just to make it a little more spooky, as we've had Halloween in just the last week or two. But if we look at, for instance, how stars are forming, this is what we think is happening when stars are forming. The star itself, this is a very young star just in the process of forming, right in the middle of this sort of hourglass, if you like. And what's thought to be happening here is material is effectively funneling down into this so-called protostar, this very early star formation. Perhaps the star is being formed, and perhaps a planetary system is also being formed right at the heart of systems like this. And again, studying the gas and dust around these stars helps us understand how these stars come to be and how the planetary systems around them come to be. But in addition to space telescopes like the Hubble and the Webb, we also need telescopes like this, the Large Synoptic Survey Telescope. A bit of a mouthful, a bit awkward. It's now been renamed the Chamonix Telescope, or the Chamonix Survey Telescope, and the acronym LSST is still used quite extensively, but it now no longer refers to the Large Synoptic Survey Telescope. It now refers to the job it's going to be doing, which is a legacy survey of space and time. That's because it is observing quite a large chunk of sky in every picture it takes, and it's going to try and cover the entire sky as seen by its location in Chile. Unlike the Hubble Space Telescope or the James Webb Space Telescope, which can only image a tiny fraction of the sky, if they wanted to cover the entire sky, it would take those telescopes a century to do that. This telescope can basically survey everything that it can see during a night, such that it can observe essentially everything in 3 nights. So remember, the Hubble Space Telescope has a tiny field of view compared to the 1/2 degree of the full moon as viewed from the Earth, but the field of view of the Large Synoptic Survey Telescope is so big I can't actually fit it on this slide. There's just a little edge of it to give you an idea of just how big an area is covered by this telescope and camera compared to the cameras of the Hubble telescope for comparison. How do you image such a large chunk of sky? Well, you start with a large mirror. There's the mirror of this particular telescope before it was figured to the right shape, before they had ground it into the dish shape characteristic of these telescopes that are used for focusing the light. So it's a single chunk of glass. You can get an idea of the scale just by looking at the people sitting around it. But catching a large amount of light is not all you need if you want to observe a large chunk of sky. You also have to think about the camera, because the camera inside, for instance, the Hubble Space Telescope has a chip in it that's approximately that big, 4 centimeters square. It's a little bit bigger than the sort of sensor you probably have in your digital camera, your SLR camera or your bridge camera. It is much bigger, for instance, than the chip that you might have in the camera in your phone, which the glass in your phone, the lens is only perhaps a couple of millimeters inside. The chip inside is perhaps only a few millimeters in size. So the chip inside the Hubble is very much larger than the chip in your phone, but the chip necessary to catch this wide angle from this telescope is very much larger. So that's not it, of course. That's just a reminder that the camera system in your phone is tiny. You can fit it on the tip of your finger there. For the same scale, That would be the size of the chip in the camera number 3 of the Hubble Space Telescope, approximately 4 centimeters, 40 millimeters on each side. Let's take that 16 million pixel chip that the Hubble has and imagine adding another 8 of the same thing into a block. Now let's take that block and add another 8, and then another 12, and then a few more for the purposes of making sure that we're pointing in the right direction and that we are correctly focused. So if that's the chip of the Hubble Space Telescope, this is a one-to-one model of the chip that's in the camera of the Large Synoptic Survey Telescope. So you can imagine how big the camera is if this is the sensor that's going to be picking up the image. 3 billion pixels, not 3 million pixels, 3 billion pixels, and it will take a picture essentially every 15 seconds for as long as the night will allow. 3 billion pixels, it'll read out in 2 seconds, it'll take a picture in approximately 15 seconds. I can't possibly show you, given that it isn't built yet, I can't possibly even show you a simulation of what that image might look like, because there's no way I can show 3 billion pixels on a screen. My laptop simply won't generate enough pixels. So just to give you an impression of what this telescope will do in a single exposure, let's just consider that tiny little black square there, a tiny fraction of the whole chip that's producing an image. In 15 seconds, we can expect to see something like that. Many, many thousands of stars, many, many thousands of galaxies, and probably a few objects in our own solar system buzzing around as well. And remember, the full image taken in 15 seconds will be 3,000 times larger than the image you're currently looking at. So this telescope is going to produce an awful lot of data. If it produces 3,000 times what you're looking at every 15 seconds, and it will do that hopefully all night, every clear night, and because it's sited in Chile on top of the Atacama Desert, most nights are clear, so it'll run almost half of the year and take pictures every 15 seconds that are 3,000 times larger than that. It's going to generate many terabytes, many thousands of gigabytes every night that it's operating, and it should operate every night for the next 10 years. So that's why it's called the survey of space and time. It's not just cataloging what's out there, it's taking pictures every few nights and it's going back to revisit the same object so we can see if things are changing. Does that star change its color? Does this object change its position? Does this object change its brightness? The telescope itself is going to be surveying hopefully everything that's out there, and it's going to try and answer certain questions. For instance, we think out there somewhere there's this enigmatic dark matter. We can't observe it, but we think it's out there. What information can we gather from looking at the entire sky that helps us work out how this mysterious dark matter is distributed through the universe? So telescopes like this will be coming along shortly. COVID has put them back a few years, but perhaps in the next 5 years, in less than 5 years, a telescope like this will be operational. The European Extremely Large Telescope, you get an idea of scale from the people standing here or the people standing outside. It is a gargantuan object. There it is to scale with all the others, roughly 40 meters in diameter. Not the largest telescope that's ever been conceived, because the red circle indicates one that was thought about some time ago. It turns out it's too expensive to build a telescope that size, 100 meters in diameter, and so they compromised by deciding to build one 40 meters in diameter. If you did build a telescope the size of the red circle, what would you call it? Because we've already built a telescope called the Very Large Telescope. We've already built one called, in the process of building one called the Extremely Large Telescope. So what do we call it? We'd call it the OWL, the Overwhelmingly Large Telescope. No money for it, but maybe it'll happen one day. So we need survey telescopes to look at the whole sky and basically tell us what's out there, catalog billions of stars, billions of objects, billions of galaxies. And we need large aperture telescopes like the Extremely Large Telescope to follow up on the interesting objects that are found. Once you've catalogued everything, you tell the big telescopes to go look in detail at some of these various objects. And you need space-based telescopes like the Hubble and the James Webb to get above the Earth's atmosphere in order to see things without the blurring effect of the Earth's atmosphere. With all of these telescopes working in tandem, hopefully we'll be able to answer a number of the questions about how the universe works. And maybe it'll prompt us to ask the questions we haven't even thought about yet. Thank you all for listening.